Thank you. So last time I was explaining what U was. So we had L equals L0 plus epsilon P. L0 is contained in L4 of V2, and P is contained in C4, C3 of T2 cross B2 cross T2. And we have, I think I was, sometimes I do it one way, sometimes I do it the other way. Yeah, I think I was taking U contained in, I'm not sure which way I did it in the previous lecture, so if I'm confusing you, speak up, I guess. C3. And then V was actually, well, okay, V is contained in R plus across this thing.
Is that V2 cross V2? U is subset of, and then
I don't know why you put 3. Okay, so actually I think I said U was, I took U and V in the same thing, but anyway, it doesn't, I mean, I took U to be positively homogeneous in this thing. And then I took V to be, so in this formulation, V is contained in R plus cross U. It's cusp residual. Yeah. Okay. So. Okay. So I wanted to say what U was. I started 2 times ago, and I told you conditions 1 through 3, and then last time I was starting on the other conditions. So conditions. Well, actually, I have a gamma. So gamma is a resonant line interval contained in R2. And then U is associated to gamma. And so I have to tell you how U is related to gamma. And so there were conditions 1 through 3. They were obtained by averaging with respect to gamma. So we have I think I call it L gamma omega equals K gamma omega plus P gamma omega. And P gamma omega P gamma omega is just the average of, applied to phi, is the average of P theta omega t for theta t contained in phi. Okay, so you remember the phi is contained in what I call T1 gamma, which is T2 cross T mod T gamma 1. So phi is a coset of this subgroup, and you average over that and so on. And then C1 through C3 had to do with the minima of P gamma phi. P gamma phi, this is a one parameter family of functions on this circle. So it's parameterized by omega, and it's defined on the circle. So P omega. So the conditions C1 through C3 were that for any given omega, these have at most two minima. The minima are non-degenerate in the sense of Morse, and then a transversality condition. So as a consequence of the transversality condition, there are only a finite number of omega for which you have a this is for omega contained in gamma. For only a finite number of omega contained in gamma, you have two minima. For the rest of the omega, you have just one global minimum. So when here I'm talking about global minima. So you have at most two global minima, and for most of them you have just one. So those are the hypotheses. Those are some of the conditions defining U. Those are the, if you like, their genericity hypotheses. So I'm saying that a typical system satisfies Arnold diffusion, and so giving C1 through C3 is part of the conditions of being typical. Okay, so now I was giving the remaining conditions, I guess C4 through C10 or something like that. They're in this thing that I handed out at the end of last hour. But let me go through them. Well, since I changed it from my original announcement, they're now C4 prime through C10 prime. So let me use that notation. Let's see. So I'm trying to remember where I was. Anyway, the remaining conditions involve looking at omega. You have omega contained in gamma, and last time I explained what it meant to admit a strong to admit a second resonance, and then among the omega which admit a second resonance, we want to consider the ones which emit a strong second resonance. So there are countably many omega containing gamma that emit a second resonance, and finitely many omega containing gamma that emit a strong second resonance. And the remaining conditions concern what happens for an omega which admits a strong second resonance. For such a thing, we have T2 omega, which is also a quotient, T2 cross T1 divided by T1 omega. And so I defined those last time. I won't repeat it. And and then we have again L omega this time equals K omega plus P omega, and P omega is well, it's given by the same formula. Well, the formula means something different here, because P omega phi. Because now phi is a coset of T omega 1. Before it was a coset of T gamma 2. So here omega is a coset of T gamma 2. No, T, I think it was T, I wrote it up. This is 2. dimension 2. And this is, let's see, T2 omega, T omega 1. I think that's the notation I use. Okay, so I have the subgroup of T2 cross T, which is T omega 1, and I take the quotient group, and then I define a Lagrangian on this, on the tangent space of this. This is the state space for the Lagrangian, and define the Lagrangian on the tangent space. So the first condition, last time I remarked that you have two on. So let's see. So the first condition is that is that p omega. I think I called this C4 omega prime. P omega has only one global minimum, and it is non-degenerate in the sense of Morse. Well, now there's more. Actually, there's more to this condition. So you have two quadratic forms on the tangent space of we'll call this global minimum m omega. So p omega has two quadratic forms on the tangent space to T2 at T2 omega to m omega. So you have the quadratic forms given by well, one of them's 1/2 L0 omega, and d2 p omega to m omega are quadratic forms on tangent space m omega of T2 omega. So you can diagonalize, and this is non-degenerate. And in fact, it's positive definite. This is the hypothesis we started out with, is that L0 is positive definite. Sorry, this is 1/2 d2 L0. So you can diagonalize this with respect to this. And actually, this is, since I assume this is non-degenerate in the sense of Morse, this is non-degenerate too. Anyway, you can find coordinates. They're just coordinates x and y, such that 1/2 L 1/2 L0 of omega L0. What do I want to say? Is this coordinates x and y such that L0 equals L0 plus let's see. Um, let's see what. Oh, I'm confused here. Anyway, I can diagonalize. So I can diagonalize so I diagonalize this with respect to. So let's call lambda and mu the eigenvalues of d2 p omega m omega with respect to 1/2 d2 L0 omega. And then we impose, so so let's forget about these coordinates. So we require as part of the condition C4 omega prime that 0 is less than lambda is less than mu. Okay, so that's the condition I wanted to say. Now, I had the new conditions in the front. That's what I'm forgetting. Okay, so okay, so I called this 1/2. I called g omega is equal to 1/2 d2 L0 omega by definition. So g omega is a flat Riemannian metric on T2 omega. So the coordinates, so there exist coordinates x and y such that g omega of m omega equals dx squared plus dy squared, and d2 p at m omega equals lambda dx squared plus mu dy squared. These are the coordinates I was referring to. Okay, so these are coordinates on T2 omega. So local coordinates on T2 omega about m omega. Okay, so once I have those coordinates, I can state the next conditions. And then I have H0 is the class of T2 T2 gamma divided by T2 omega. Well, it's defined up to sign, but the sign doesn't matter. So this is contained in T2 divided by T2 gamma divided by T1 omega. It's contained in H1 H1 of T2, no, T2, yeah, T2 gamma divided by T1 omega is contained in H1 of T2 with coefficients, which is contained in H1 of T2 omega with coefficients in R. So normally I think of this as a class in here. And then, I have the condition C 5 omega prime which is that there's only one GE0. Did I define GE0? And then we have the Jacobi matrix GE, which is defined to be, I think it's 2. For some reason there's a factor of 2. I don't remember why. 2k omega plus 2p omega plus e k omega well, this is definition other than the factor. I never know the factor. Anyway, the factor doesn't matter. I think this is g omega. Whatever. It only changes the factor. So, okay. So this is a Jacobi metric. It's defined for E contained in R, and it's relevant actually only for E greater than or equal to E0, and E0 is defined to be minus g omega of m omega. Minus p omega of m omega. Okay, so if E is greater than E0, then this is a Riemannian metric for E greater than E0, and it degenerates at m omega for E equals E0. Okay, so I think I got as far as this condition C5 omega last time, but I'll repeat it, which is that there's only one shortest curve is only one GE 0 shortest curve in H0. Okay, so by this I mean, so H0 is a homology class, first homology class. So to say the curve is in let's say closed curve. So, I mean, if you have a closed curve, of course, it defines a homology class. So to say that the closed curve is in the homology class means that that's the homology class that it defines. Okay, so there are three possibilities. Let me make my notation consistent with what I wrote in the note in the paper you have. So this was not m omega, it was n omega. Okay, so change m omega to n omega everywhere. Um, okay, so 3 possibilities. Gamma 0, so I call this curve gamma 0. Is simple and passes through n omega. And sorry, and does not pass through. Gamma 0 is simple and passes through n omega. And gamma 0 is not simple. In this case, gamma 0 equals p gamma 1 plus q gamma 2, where gamma 1 and gamma 2 are simple and pass through n omega. P is greater than 0, q is greater than 0. P and q are relatively prime. If I set H to be the homology class of gamma 1 and H2 to be the homology class of gamma 2, then H1, H2 generate the group H1 of T2 with coefficients in Z. This is T2 omega. Okay, so that's C5 prime. And then you have condition C6 omega prime, which is that if the GE0 shortest curve in H0 is simple, then and passes through n omega, then it is tangent to the x-axis at n omega. If it's not simple, gamma 1 and gamma 2 are tangent to the x-axis. At n omega. Okay, so this perhaps requires some explanation. the um, so here, first of all, x and y are the coordinates. X and y are these coordinates. And now, what happens is that actually, under the hypothesis C4 omega prime, it follows that if you have so there's a lemma, I guess you call it, a lemma that if there exists a C1 curve C through n omega in T2 omega, such that if P is contained in T2 omega is in a sufficiently small neighborhood of n omega, then there's a unique shortest curve connecting P to n omega. And if P is contained in C, this curve is contained in C. And I should say that curve C is tangent to the y-axis. And otherwise, the shortest curve is tangent to the x-axis. Yeah.
What do you mean by if P belongs in C, that this curve is contained in C?
The shortest curve.
Ah, the shortest curve. Okay, okay.
So I have, so the picture is this. I have, here's the y-axis, here's the x-axis, here's C. If I start with a point P contained in C, the shortest curve is contained in there, and otherwise the shortest curve is tangent to the x-axis.
For this, you need lambda and mu to be separated.
Yes. And this is actually a rather easy consequence of something you probably know well from dynamical systems. What you do is you see such a you go back to the original system. I'm now talking about a Jacobi metric, and I'm talking about the shortest curves with respect to the Jacobi metric. And the Jacobi metric is associated to a Hamiltonian system. As you know, the curves under the Hamiltonian system correspond to the curves, the geodesics of the Jacobi metric. So these shortest curves correspond to some curves of the original system. Now, in the original system, you have what's called you have a hyperbolic critical point. The point n omega 0 contained in T2 was not really the original system. It's the average system. It's the L omega system. L omega. So n omega 0 contained in tangent space of T2 at n omega. or just tangent space, is a hyperbolic critical point is rest point. Let's call it rest point of well, I'll say of L omega. Of course, what I mean is of the Euler-Lagrange equation associated to L omega, of L omega with eigenvalues plus or minus lambda and plus or minus mu. So there are 4 eigenvalues. And there are 2 negative eigenvalues, so they give you the stable manifold. So you have a 2-dimensional stable manifold, and these shortest geodesics are just the orbits on the stable manifold which converge to the origin, which tend to the origin. So, and these properties are a standard property of such dynamical systems. So anyway, I wrote this up, and I brought copies of what I wrote here. It's written up and published in this Proceedings from Nankai, which was mentioned in the references of this other paper that I handed out last week. So anyway, this is not very difficult to prove if you know dynamical systems. Okay, so this explains 6 omega prime. This explains why 6 omega prime is a generic condition. I mean, all but one of the curves are tangent to the x-axis. Now, what I'm saying is that the shortest curve, so I'm saying there's only one. I'm making as a hypothesis, or rather, it's part of the definition of U, or if you like, it's a genericity condition. Is that there's only one shortest curve in the class, and now if that's simple and passes through n omega, I'm making the further condition that it's tangent to the x-axis. The only other possibilities, well, it could be tangent to the y-axis, or it could be, or it could have a corner, but I exclude those possibilities by hypothesis, by part of the definition of U, and then I say that the things I've excluded is a nowhere dense set, nowhere dense closed set, I guess, and that's basically it's because of this lemma that's nowhere dense set. Okay, so that's the condition 6 omega prime. Now. Now, another condition I need is, well, it's a generalization of condition of being non-degenerate in the sense of Morse to this situation. I mean, you can say that shortest curve is non-degenerate in the sense of Morse. Or I'll go. Well, maybe I should say that right now. So, if I have a shortest curve which doesn't pass through n omega, then you know what it means to be non-degenerate in the sense of Morse. There are various ways to define it, but one way is to take a transversal and you take orbits, you take shortest curves passing through points on the transversal and in the same homology class. So if you have a point on the transversal, there's a shortest curve in the homology class which passes through that point. And it has a length. And the length is, well, I'm assuming everything is CR, so the length is a CR function of, I mean, I'm assuming P and L are CR. So it follows that the length is actually a CR function in the neighborhood of the intersection point, in a sufficiently small neighborhood of the intersection point. And you say that that the original closed curve is non-degenerate. One condition, necessary and sufficient condition for the curve to be non-degenerate in the sense of Morse, is that this distance function, this length function, as a function of the point on the transversal, has a non-degenerate minimum at the intersection point. Okay. So I'll take that condition as the condition for if I have a simple closed curve passing through in omega, I'll take that same condition as the condition for the simple closed curve to be non-degenerate in the sense of Morse. Actually, there's difficulty in proving that this function is actually C2 in the neighborhood of the intersection point, but I think I proved that. So anyway, so the condition. So now we can state condition C7 omega prime. Which is that if the GE0 shortest curve, well, if I don't need to repeat those words. If gamma 0 is simple, then it is non-degenerate in the sense of Morse. And otherwise, gamma 1 and gamma 2 are non-degenerate in the sense of Morse. So, yeah, I should say the condition of being C2 in the neighborhood of the intersection point seems to require completely different proof from the classical case. This is something. I'm not going to describe it now.
Can you repeat what is non-degenerate in the sense of Morse here? I didn't really understand.
Okay, so I just repeat the definition, except that now I have a point in omega on this simple closed curve. And now I have so I have the shortest geodesic on this. And now if I take a point, so I choose a transversal to the curve. And now if I take a point on the transversal, I can take a shortest curve in H0. And now actually the shortest curve in H0 passes through n omega if the point's close enough to the intersection point. I can take, so it passes through in omega, and anyway, I take the length of this curve. So that's a function of the point on the transversal. And then there's a theorem that this function is C2 in the neighborhood of the intersection point, which, as far as I can see, is a difficult theorem to prove. But and it's the classical method doesn't work. But anyway, and then I say that that function has the minimum of that function at this intersection point is non-degenerate. So if the minimum of that function at this intersection point is non-degenerate, then I say that the simple closed curve is non-degenerate in the sense of Morse. Okay, is that?
If the orbit is hyperbolic, is it non-degenerate in the sense of Morse?
Well, let's see. So it's
Can you give a simple example?
yeah, it's not an orbit really. I mean it's
As a curve.
as you see, you can consider it. You can consider it as an orbit of the Lagrangian system, of the average Lagrangian system, L omega, and as such an orbit, it's a homoclinic orbit to this thing. Let's see. Maybe there's a standard definition of homoclinic orbits being hyperbolic. Maybe I could use that definition. It just occurred to me, rather than fussing. So it's homoclinic. Anyway, it's as an orbit of as a geodesic, it's only finite length, so it ceases to be defined when you get to n omega. Okay, so that's okay. Now the other conditions are conditions on conditions on GE for E greater than E0. So we let E0 hat greater than E0, let's say much greater than E0, depend on L0p and omega. So we're going to just choose. So choose this. Choose. So we choose it large enough for what I'm going to say to be true. And then if and then also E0 in the case gamma 0 is not simple, choose E0 star greater than E0, only a little greater. And again, what I say is, see, I'll define U depending on E0 hat and E0 star, and then when I say if I choose E0 hat large enough and E0 star small enough, then the theorem is true with the U I'm defining. So I'm defining U, but U depends on these choices. So, so the condition is that each GE shortest curve in H0 is non-degenerate in the sense of Morse. For E0 hat greater than or equal to E0 is greater than or equal to E0, in the case that gamma is simple, gamma 0 is simple.
This is star missing
Um,
for E at zeros.
and no,
Or you write E0 bigger than E0, so I think the middle one needs a star.
sorry. This is E. E. E0 star okay, so I need to put different conditions in the different cases in order for the theorem to be true with this definition of U. And C9 omega prime there are at most two simple closed curves in H0 for E0 hat greater than or equal to E greater than or equal to E0. In the case gamma 0 is simple. So gamma 0 is the shortest curve associated to GE0. And for E, same conditions, E0 hat greater than or equal to E greater than or equal to E0 star. In case gamma 0 is not simple. And C10 omega prime is a transversality condition. So C10 omega prime is that we have we suppose E0 hat is greater than or equal. So, suppose E0 hat is greater than or equal to E1 greater than E0, simple case, or E0 hat is greater than or equal to E1 is greater than or equal to E0 star, not simple case. And there are two shortest GE0 curves, two GE1 shortest. In H0. We'll call them gamma and gamma prime. Then our condition is that the derivative of LE with respect to gamma E with respect to E, evaluated E equals E1, is not equal to the derivative of LE gamma prime E dE, evaluate E equals E1. Here, of course, LE equals the GE length. And gamma E and gamma E prime are continuations of gamma and gamma prime. Okay, so that's the third condition. So, okay, so I've explained the conditions defining U. The last three conditions are analogous to the first three conditions. See, instead of in the first three conditions, C1 through C3, I gave conditions for conditions on the function p gamma omega. So this is a one-parameter family of functions depending on omega, and the minima of this had to satisfy those three conditions, C1 through C3. So the minima had to be non-degenerate in the sense of Morse, and it had to be at most 2 for each value, and then you had the transversality condition. Well, these are the same three conditions, but instead of for the minimum of this function, it's for the shortest curves of this Jacobi metric. It's basically the same conditions, just stated for the shortest curves of the Jacobi metric in place of the minima. Here there's also a parameter, namely E. So you have a one-parameter family again. And so whenever you have a one-parameter family, you can impose those conditions. So I've done it twice. Okay, so I guess my time's up for today. But, I'm sorry I haven't given you any proofs or anything. But